There is a planet twice the size of Earth where it rains diamonds. Not metaphorically, not as a poetic description of something that merely resembles diamonds under certain conditions. The leading scientific models for the interior of this world describe literal diamond precipitation, carbon crystallizing under extreme pressure, forming solid gemstones that fall through liquid diamond oceans and accumulate on a diamond mantle surrounding a dense, solid diamond core. A world made almost entirely of the hardest natural substance known to exist. A world where the most valuable material in human civilization is so abundant it forms the ground, the ocean, the rain, and the sky. Its name is 55 Cancri e. It orbits a star 40 light-years from Earth, and the story of how we found it, what we think it is made of, and what it means for everything we thought we understood about planets is one of the strangest journeys modern astronomy has taken. But 55 Cancri e is not the only diamond world we have found, and the deeper you go into the physics of how diamonds form inside planets, including the planets in our own solar system, the more the universe starts to look like something that was designed to produce them everywhere, constantly, in quantities so vast that the word rare becomes almost meaningless. First, let's establish what a diamond actually is. A diamond is carbon, pure carbon, arranged in a specific crystalline lattice structure, each carbon atom bonded to 4 others in a tetrahedral pattern that makes the resulting solid extraordinarily hard and extraordinarily stable. The conditions required to form diamond naturally are high pressure and high temperature. Specifically, pressures exceeding around 45 kilobars and temperatures above roughly 900 degrees Celsius. On Earth, those conditions exist in the mantle, approximately 100 to 200 kilometers below the surface. Diamonds form there slowly, over millions to billions of years, and are occasionally carried upward to the crust by volcanic eruptions through structures called kimberlite pipes. The diamonds in your jewelry were formed in the Earth's mantle, carried to the surface by ancient volcanoes, mined from rock, cut by human hands. They are, in one sense, completely ordinary products of planetary physics. In another sense, they are a clue, a signal that wherever you find the right conditions, the right pressure, the right temperature, the right chemistry, diamonds are not a miracle. They are an inevitability. And the universe, it turns out, has the right conditions in a great many places. 55 Cancri e was discovered in 2004. At the time, it was remarkable for one simple reason. It was one of the first super-Earths ever detected. A rocky planet, approximately twice Earth's diameter and about 8 times Earth's mass, orbiting its star at a distance so close that its year lasts only 17 hours and 23 minutes. 17 hours. One complete orbit of its star in less than a single Earth day. At that distance, the surface temperature on the side facing the star is estimated at approximately 2,000 degrees Celsius, hot enough to melt rock, hot enough that the surface may be partially or fully covered in a magma ocean, liquid rock flowing across a world that completes its orbit before most people finish a working week. But the temperature and the orbit were not what made 55 Cancri e extraordinary. What made it extraordinary was the star it orbits. 55 Cancri, the star, is rich in carbon relative to oxygen. This ratio matters enormously for what kinds of planets form around it. In our own solar system, the Sun has more oxygen than carbon. This means the rocky planets that formed here, Earth, Mars, Venus, Mercury, are oxygen-dominated in their mineralogy. Silicate rocks, iron oxides, water ice. The chemistry of our solar system is fundamentally oxygen chemistry. Around a carbon-rich star, the chemistry shifts. Carbon-dominant minerals form instead. And when planetary scientists modeled what a rocky super-Earth would look like if it formed in a carbon-rich system under the pressure and temperature conditions that 55 Cancri e would experience,
The result was unambiguous. The planet would be made primarily of carbon. At the pressures generated by a world 8 times Earth's mass, that carbon would be compressed into diamond. Not everywhere, not at the surface, which is too hot and under too little pressure for diamond stability, but in the deep layers, where pressure climbs to millions of atmospheres. Diamond is exactly what the physics predicts. A diamond mantle, a diamond core, a planet where the most coveted substance in human history is the structural foundation of the world itself. But here is where the story becomes stranger. In 2012, a follow-up study of 55 Cancri e revised the estimates of the star's composition. The carbon-to-oxygen ratio, it turned out, was not as extreme as initially thought. The planet might be less diamond-dominated than the original models suggested. The scientific community pulled back slightly from the most dramatic claims. And then, in 2023, the James Webb Space Telescope observed 55 Cancri e directly, capturing thermal emission data from the planet's surface with a precision no previous instrument could achieve. What it found was unexpected. The temperature distribution across the planet did not match what a bare rock world with a magma ocean would produce. The data suggested the presence of a volatile atmosphere, gases, possibly carbon dioxide or carbon monoxide, possibly something stranger, redistributing heat across the surface in ways that only an atmosphere can. A world that was supposed to be a bare, molten rock turned out to possibly have air. We do not know what that atmosphere is made of. We do not know whether it is stable or whether it is constantly being replenished by volcanic activity. We do not know whether the interior is truly diamond-dominated or whether the revised stellar composition estimates change the picture more than we currently think.
What we know is that 55 Cancri e is not simple. It is a world that keeps revealing new layers of complexity every time we look at it more carefully. And the diamond interior remains one of the leading models for what lies beneath whatever is happening on its surface. Now let's leave 55 Cancri e and come back to our own solar system, because it turns out we may not need to travel 40 light-years to find diamond worlds. Neptune and Uranus, the 2 ice giants at the outer edge of our solar system, are not well understood. Of all 8 planets, they are the least studied. Only 1 spacecraft has ever visited either of them. Voyager 2 flew past Uranus in 1986 and Neptune in 1989, spending only hours near each planet before continuing outward. We have not been back since. What we know about their interiors comes primarily from models, from calculations based on their masses, their densities, their magnetic fields, their rotation rates, and laboratory experiments that attempt to recreate the extreme conditions inside them. Those models predict something extraordinary. At depths of roughly 10,000 kilometers inside both Neptune and Uranus, the pressure reaches approximately 2 million atmospheres. The temperature reaches 5,000 to 7,000 degrees Celsius, and the material at those depths is a mixture of water, ammonia, and methane, all compounds containing carbon and hydrogen, compressed under conditions that fundamentally change their chemistry. Under those pressures, methane breaks apart. The carbon atoms are freed from their hydrogen bonds and compress into something else entirely: diamond. The leading models for Neptune and Uranus suggest that both planets may contain enormous quantities of diamond in their deep interiors. Some models propose that diamond forms continuously, crystallizing from the high-pressure carbon soup, sinking through a denser liquid layer, accumulating over billions of years in a growing solid diamond core. Diamond rain, not as a metaphor, as a planetary process that may be occurring right now in 2 worlds that have been orbiting our own sun for 4.5 billion years, so close that you can see them through a small telescope on a clear night. Laboratory experiments have confirmed the underlying physics.
In 2017, researchers at the SLAC National Accelerator Laboratory in California used high-powered lasers to recreate the pressure and temperature conditions of Neptune's interior in a sample of polystyrene, a plastic that contains carbon and hydrogen in similar proportions to the compounds in Neptune's deep atmosphere. They compressed it to approximately 1.5 million atmospheres using laser-driven shock waves. They heated it simultaneously to thousands of degrees. The carbon atoms in the polystyrene separated from the hydrogen. They compressed into tiny diamond crystals, nanodiamond particles, measurable and confirmed, that formed within nanoseconds of the pressure wave passing through the material. The experiment worked. The physics is real. Diamond formation under those conditions is not a theoretical prediction, it is a measured result, replicated in a laboratory, confirming that what the models say is happening inside Neptune and Uranus is physically possible. The solar system may contain 2 diamond-raining worlds. We just haven't been able to look closely enough to confirm it yet. And this is where the scale of it starts to become genuinely difficult to process. The diamond in a typical engagement ring weighs about 1 carat, half a gram. It took approximately 1 to 3 billion years to form in the Earth's mantle, was carried upward by a volcanic eruption, survived millions of geological processes before being mined, cut, polished, and set in metal. Its rarity, the thing that gives it value, is entirely a function of the narrow conditions under which it forms on Earth. Inside Neptune, diamond is not rare. Diamond is weather. The quantities involved in planetary diamond formation are beyond any scale that makes economic sense to discuss. A single diamond precipitation event inside Neptune, carbon crystallizing and falling through a liquid diamond layer over geologic time, would produce more diamond than the entire global reserve of gem-quality stones on Earth, multiplied by 4.5 billion years. The universe is not careful about producing things we consider precious. It produces them wherever the conditions are right, in quantities that dwarf everything human civilization has ever assigned value to, in places we cannot reach and will not reach for generations, if ever. There is a star, BPM 37093, nicknamed Lucy after the Beatles song, located about 50 light-years from Earth. It is a white dwarf, a dead star, a cooling crystallized remnant of a sun-like star that exhausted its fuel and shed its outer layers billions of years ago. White dwarfs cool slowly. As they cool, their carbon and oxygen cores crystallize. The entire interior of the star solidifies into a crystal lattice. BPM 37093 has cooled enough that astronomers estimate its core has crystallized significantly. The crystal is carbon under the pressure of stellar gravity. The core of this dead star is, by every physical definition, a diamond roughly the size of Earth's moon. A diamond roughly 4,000 kilometers across, with a mass roughly 500 times the mass of Earth, orbited bone-nothing, going nowhere, sitting 50 light-years away, cooling in the dark, a stellar remnant that human beings named after a pop song, because the alternative, sitting quietly with what it actually is, felt like too much. We have spent most of human history treating diamonds as symbols of permanence, of value, of love that does not end. We mined them from rock with enormous effort and expense, cut them with precision instruments, exchanged them at pivotal moments in human lives as tokens of things that matter. And all of that meaning was constructed on top of a physical fact that the universe has been indifferent to for billions of years. Carbon, under pressure, becomes diamond. Everywhere, in the mantles of rocky planets, in the deep interiors of ice giants, in the cooling cores of dead stars, in the carbon-rich worlds around stars nothing like our sun. The universe does not know that we value these things. It produces them not for us. It produces them because physics demands it, because the conditions that make carbon compress into that specific crystalline lattice exist in so many places, at so many scales, that avoiding diamond would actually be harder than making it. We looked up at the sky and found the most precious thing we knew reflected back at us in quantities that make the word precious meaningless. And somewhere in that, in the distance between what we thought was rare and what the universe treats as routine, there is something that says more about us than it does about the cosmos. We decided what was valuable before we knew what was common. We built our symbols out of physics we didn't understand yet, and the universe, indifferent and vast and endlessly productive, kept making diamonds in the dark, billions of years before we arrived to want them, and will keep making them long after we are gone.